earlier on, we talked about Kirchhoff's rules. We talked about when a current flows into a point in a wire, do we have the same current flowing out? And so if the exception I mentioned earlier was that if I have a capacitor, I can have a current flowing onto a plate and then I have a current flowing off the plate, but there's this gap in between. So how do we deal with that? So what I want to do is I want to create a Gaussian surface around this plate right here. I know that the electric field between the plates is sigma over epsilon sub naught. Q is the charge divided by the area of the plate. So this is Q over A epsilon sub naught. If I multiply both sides times the area, I get EA is equal to Q over epsilon sub naught. And we'll take it one step further. Epsilon sub naught EA is equal to Q. So I have this E right here, again, is the magnitude of the electric field. So if I take the change of Q, that would also be the change in epsilon sub naught EA. For non-calculus space, delta Q is equal to delta epsilon sub naught EA. For the non-calculus group, this is generally it's a change, it's a macroscopic change. It's some noticeable change, and the D just stands for infinitesimal change. Well, the area of the plates and epsilon sub naught are constants, so they can come out. So dq is equal to epsilon sub naught A dE. And then if I divide by the change in time, then I have epsilon sub naught is equal to, well, that right there is the change in the electric flux. I probably should combine it at that point, is equal to this current. Now, this is not a traditional kind of current. This current is known as the displacement current. So usually a little d gets put in down there, so displacement current. And so we have this traditional current flowing onto it, and then the displacement current flowing off in between the two plates. And this is how we still maintain Kirchhoff's current rule. But recognize, since we have two currents here, we need to take that into account. If we look at Ampere's law, B dot dl is equal to mu naught I, or the sum of all the B dot delta L's is equal to mu naught I. This current, we have to take both into account. So this now gets expanded, I plus I sub d. So we have a modified version of Ampere's law. This is Ampere's law with Maxwell's correction. And if I make this substitution here into it, I get the integral of B dot dl is equal to mu naught I, the traditional charge moving current, plus mu naught epsilon sub naught d phi e dt, or the sum of B dot delta L around the closed loop is equal to mu naught I plus mu naught epsilon sub naught delta phi E delta T. We now have all four of Maxwell's equations, and that will be the next video.